Hi, myself Dr. Vindra Kumar. Today in this session, we will discuss about the dynamic programming. Dynamic programming is mainly an optimization over plain recursion. Whenever we see a recursive solution that has repeated call for the same inputs, we can optimize it using dynamic programming. The idea is so simply to store the results of subproblems so that we don't have to recompute them when needed later. The simple optimization reduces the time complexity from exponential to polynomial. Before moving on to understand different methods of solving the dynamic programming problems, let's first take a look at what are the characteristics of a problem that tell us we can apply the dynamic programming to solve it. First is overlapping subproblems and second is optimal substructure property. In first one, overlapping subproblems. Like divide and conquer, dynamic programming combines solution to subproblems. Dynamic programming is mainly used when solutions of same subproblem are needed again and again. In dynamic programming, computed solutions of subproblems are stored in a table so that these don't have to be recomputed. So dynamic programming is not useful when there is no common overlapping or subproblems, because there is no point to storing the solutions if they are not needed again. Take an example of Fibonacci number. To find the Fibonacci 4, we need breakdown into the following subproblems. For the Fibonacci 4, we divide the Fibonacci 3, Fibonacci 2. Fibonacci 3 is again divided into the Fibonacci 2, Fibonacci 1. Fibonacci 2 is divided into Fibonacci 1, Fibonacci 0. And here, this side Fibonacci 2 divided into Fibonacci 1 and Fibonacci 0. We can clearly see the overlapping subproblems pattern here, as Fibonacci 2 has been evaluated twice and Fibonacci 1 has been evaluated 3 times, and same the Fibonacci 0 is evaluated 2 times. On another side, in optimal substructure property, a given problem has optimal substructure property if the optimal solution of the given problem can be obtained using optimal solution of its subproblem. Like here Fibonacci n, then Fibonacci n is equal to Fibonacci n minus 1 plus Fibonacci n minus 2. This clearly shows that the problem of size n has reduced to subproblems of the size n minus 1 and n minus 2. Therefore, Fibonacci numbers have optimal substructure property. There are two approaches of dynamic programming. The first one is the top-down approach and the second one is bottom-up approach. Let's take closer look at both approaches. So first is top-down. In this approach, we try to solve the bigger problem by recursively finding the solution to smaller subproblems. Whenever we solve a subproblem, we cache its results so that we don't end up solving it again if it's called multiple times. Instead, we can just return the saved result. This technique of storing the results of already solved subproblems is called memoization. In bottom-up approach, or say in tabulation, is the opposite of the top-down approach and avoid recursions. In this approach, we solve the problem bottom-up by solving all the related subproblems first. This is typically done by filling up an n-dimension table. Based on the results in the table, the solution of the top or original problem is then computed. Tabulation is the opposite of memoization. As in memoization, we solve the problem and maintain a map of already solved subproblems. In other words, in memoization, we do it top down in the sense that we solve the top problem first. So to more understanding about the dynamic programming, we take an example of Fibonacci number. In the Fibonacci numbers are often defined recursively. Recursion means a function call itself. In the code, Fibonacci function call itself with a lesser value and again. In math, the Fibonacci sequence is described as the sequence of numbers where the first two numbers are 0 and 1, with each subsequent numbers being defined as the sum of previous two numbers in the sequence. In this program, Fibonacci series is calculated using recursion with the seed as 0 and 1. Each time a recursive call is made to Fibonacci method, the current state or instance of the method is stored in memory, or can say stack, and a new value is passed to the method for the next instance of the method to use. As each term is resolved to the value 0 or 1, the previous instance of the method can be resolved to an actual value. The result is that line of code Fibonacci n-1 plus Fibonacci n-2 can now be resolved by adding the two values. This result is then returned to the previous instance of Fibonacci method in order to again help with the line code resolved to actual value in that instance. The adding of two terms continue in this manner until all the terms in the equation is resolved to actual values, with the total then returned to the code with called the Fibonacci method in the first place. And termination condition is very important for recursion function. Here, that is n is equal to 0 and n is equal to 1, or the recursive call would be infinite, leading to the stack overflow error. But this is not efficient solution to calculate the Fibonacci with the simple recursion method. On another hand, using the dynamic programming, the way we solved the Fibonacci series was the top-down approach. We also used the term memoization, a word derived from the memo for this. In other terms, it can also be said that we just hit the problem in a natural manner and hope that the solution for the subproblem are already calculated, and if they are not calculated, then we calculate them on the way. Top-down uses memoization to avoid the recomputing the same subproblem again. Let's solve the same Fibonacci problem using the top-down approach. Top-down starts breaking the problem unlike the bottom-up. Like if we want to compute the Fibonacci 4, the top-down approach will do the following: Fibonacci 4, go to the compute Fibonacci 3 and Fibonacci 2 and return the result. Now Fibonacci 3, go to the compute Fibonacci 2 and Fibonacci 1 and return the result. Fibonacci 2, go to the compute Fibonacci 1 and Fibonacci 0 and return the result. Finally, Fibonacci 1 will return 1 and Fibonacci 0 will return 0. On another way, we could have solved the Fibonacci problem by using starting from the bottom. This is the bottom-up approach. Start by calculating second term and third term and so on, and finally calculate the higher term on the top of these, that is by using these values. We use term tabulation for this process because it is like filling up the table from the start. So here we have code for the Fibonacci series using bottom-up approach. So finally we see the memoization and tabulation, what the similarities and what the difference between these. Both memoization and tabulation solve individual subproblems only once. Memoization uses recursion and works top down, whereas tabulation moves in opposite direction, solving the problem bottom up. Memoization is needed the natural way of solving problem, as coding is easier in memoization when we deal with the complex problems. Coming up with specific order while leading with the lot of conditions might be difficult in the tabulation. Also think about a case when we don't need to find the solution of all the subproblems. In that case, we would prefer to use memoization. However, When a lot of recursive calls are required, memoization may cause memory problem because it might have stacked the recursive calls to find the solution of the deeper recursive call. But we wouldn't deal with this problem in tabulation. Generally, memoization is also slower than the tabulation because of the large recursive calls. So, in both are applicable to problems with overlapping subproblems. Memoization perform comparatively poor as compared to the tabulation due to the overhead involved during the recursive function calls. Thank you.
The topic is matrix chain multiplication using dynamic programming. Now, before starting with matrix chain multiplication, the question comes in mind, what is dynamic programming? As you might As you know, what is divide and conquer approach? Divide and conquer approach used to solve an instance of a problem by dividing it into smaller instances and then blindly solves these smaller instances. Once you got the results from these smaller instances, those results are further being utilized to give the final answer. Now what problem is faced in divide and conquer algorithm? Divide and conquer algorithm often ends up repeatedly solving some common instances. Like if you see here, when you are applying divide and conquer, that is, you are solving any problem, say Fibonacci series using recursion algorithm. So here, if you can see, if you go for tracing that recursive algorithm, you can see Fibonacci series for f is equal to 3 is being computed 2 times. Similarly, Fibonacci 2 is also being computed 2 times, and so on. The problem in divide and conquer is sometimes these many common instances are repeatedly being solved in this. Dynamic programming is similar to divide and conquer in that an instance of a problem is divided into smaller instances. However, in this approach, we solve small instances first, store the results of those small instances, and later whenever we need a result, we look up at those stored results rather than recomputing them again. Now, in a dynamic programming algorithm, we usually construct a solution from a bottom up in the form of array. That is why dynamic programming is generally called a bottom up approach. Now, if you go for the major steps of dynamic programming algorithms, first we will establish a recursive property that gives a solution to an instance of problem. That means we will first go for a recursive feature of that problem, and then we will solve an instance of problem in a bottom up fashion by solving smaller instances first. Matrix chain multiplication. Let us just do some preliminary concept. Now what is the if you want to multiply if you want to multiply two matrices, say as given shown in the example, the column of the first matrix and the row of second matrix should be same, only then multiplication is feasible, and the resultant matrix after these two multiplication will be 2 by 3, that is the row of the first and the column of the second matrix. Similarly, for the second example, we can see the second example, that means compatibility of this column of this and row of the second matrix should be same, and the resultant matrix will be 3 by 1. Now, one more thing is that if you want to do any matrix multiplication, let us suppose you are multiplying two matrices of dimension 2 by 3, second is 3 by 2, and the resultant matrix obviously will be of dimension 2 by 2, that is the row of the first and the column of the second matrix. Now, during this matrix multiplication, if you go in detail of these, how many number of multiplications which are required to multiply these two matrices? This is the being required to multiply these two matrices. Now, if you go detail into this matrix multiplication, you can count the number of multiplication 1, 2, and 3. Similarly, 3 here, 3 here, 3 here, and 3 on the upper end. That means total 12 multiplication. 3 multiplied by 4 multiplications These are elementary multiplications which are being used to multiply a given matrix A and B. Now 12 multiplications are there. If you want to directly find the number of multiplication without going into this detailed concept, that is number of rows of A multiplied by number of columns multiplied by the number of columns of B. That means rows of A, this is a common dimension, and columns of B. This too will lead, we want to conclude from these slides that if two matrix are there A and B with dimension 2 by 3 and 3 by 2, and if you are multiplying these two matrices, and the total number of multiplications, the elementary multiplications which are being involved during the multiplication of these two matrices are 2 into 3 into 2. That is, this is the common dimension which will be used once for finding the number of multiplication. This is also called cost of multiplication. Cost of multiplication is nothing but the number of multiplications which are being required to multiply two matrices. Now, one more thing being there in matrix multiplication, that matrix multiplication is an associative operation. Now, consider this chain of matrix multiplication. If you multiply the matrix in this form or in this form, in both the forms, answer is the same one. Like if you first multiply CD, then you multiply the result of CD with B, then you multiply finally A. What result you are getting from here will be same as that of as that on the right hand side. Now in this case you are first multiplying the matrices A and B together, and then you are multiplying C and D together, then you are multiplying the output of these two together. That means both the answers are going to be same. This says a matrix multiplication is associative operation. This implicitly says that the order of in which we are multiplying the matrices does not matter. It will yield to the. This slide represents that how the order of matrix multiplication can affect the count of total number of multiplications for that very scenario. For example, if you want to multiply three matrices in sequence, if you are using this form of matrix multiplication, the total number of multiplications you encountered will be 7500. And if you are following this other form of matrix multiplication, then here the number of multiplication will be 75,000, which is roughly 10 times larger than the previous order of multiplication. Both the patterns are going to give the same answer, but this is more efficient one, 10 times faster than the previous one. The reason being this is how to find the count of multiplications here. When we are multiplying a1 with a2, we are getting the count of multiplication as 10 into 100 into 5. This is the first one. And when we are multiplying a1, a2, the final dimension of the matrix of a1, a2 after multiplication will be 10 into 5. This will become 10 into 5. When we are multiplying 10 by 5 matrix with 5 by 50 matrix, the cost of multiplication will be 10 into 5 into 50. So the resultant, do the sum up of these two, you will be getting the answer as 7500. Now considering the second case, if you are going to multiply this a2 and a3 first, the cost of multiplying a2 and a3 will be 10. Now considering this case, when you are multiplying a2 and a3 first, the cost of multiplying a2 and a3 will be 100 into 5 into 50. And the dimensions of a2 and a3 will become 100 and multiplied by 50. Now if you are multiplying the result of a2 a3 with a1, then cost of multiplying these two partial matrices will be 100. This is dimension of this a1 is 10 into 100, and dimensions of a2 is 100, a2 a3 is 100 into 50. Then answer will be 10 into 100 into 50, 10 into 100 into 50, and that this will result into 75,000. What this we want to conclude from this slide is that order greatly affects the count of multiplication, which implicitly decreases the running time of the algorithm to calculate the matrix multiplication. Now this is one more example where we want to multiply this chain of matrices, and with the dimensions whose dimensions are being given here, and there are 5 different orders in which these matrices 4 matrices can be multiplied. These are different orders. First CD is being multiplied, then it is multiplied further by B. This partial matrix result is being further multiplied by A. In this case, BC is first multiplied, then the resultant matrix of BC is multiplied by D, then this partial result is further multiplied by A, and so on. Here A and B are multiplied first, then C and D are multiplied after that, then these two matrices are further being multiplied. Now, after counting the number, you can now count the number of multiplication by using the same formula, and you can just see out of all these five possible different orders, this order is giving the optimal number of matrix multiplication count. Now it is better clear to you what we were trying to achieve here. The goal of matrix chain multiplication is to determine the optimal order of multiplying and matrices. Here, if you want to give a formal definition of the same, that means given a chain of matrix multiplication a1, a2 till an, and there with having dimensions pi minus 1 to pi, and we want to parenthesize the product, or we want to order the matrix multiplication ordering is, and we want the order which according to which the matrix should be multiplied such that the total number of scalar multiplications are minimized. One point to be noted here we are not actually multiplying the matrices, we are just relying on counting the number of multiplications. Now suppose this matrix is given, now from algorithm point of view, let me just explain what sort of terms we are going to use. Now if you are multiplying these matrices, dimension of this will be given 5 by 2. Obviously this will be 2 only, because these two should match if you want to multiply consecutive two matrices, and so on. The dimensions of individual, let us suppose considering the matrix A4, it will have the dimension labeled as P3 and P4. That means in general case, if for a given matrix AK, the dimensions of that will be Pk minus 1 multiplied by, if you generalize this for a given matrix, the dimensions of the same will be pk minus 1 and pk. That means pk will be the number of rows and pk minus 1 is the number of columns. For matrix ak minus 1, the previous of the ak, the dimensions will be pk minus 1 and pk minus 2. This is the representation which we will be using for writing the algorithm part of that chain of matrix multiplication problem. Now going further, now as you can see, if you are this is a chain of matrix multiplication. If you are merely concentrating on this part of matrix multiplication, that means you want to multiply a4 multiplied by a5 multiplied by a6. Now there are two ways to implement this. There are two ways to implement this concept. That is, first you multiply a4 and a5, then the resultant is multiplied by a6, or you multiplied a5 and a6 first, then multiply the result by a4. Now the number of multiplication in the first case, if you count, that is 392. Number of multiplication in the second case is 528. Now what is the optimal number of multiplication? Take the minimum of these two. So optimal number of multiplications, that means minimum number of multiplications which are required to multiply the matrix A4 into A5 into A6 is 392. Now how to represent the same using algorithm point of view? We are using an array, two-dimensional array. Let the name of the array is given as M. Here four row value and column value 6 represents that we are giving the cost value or the count of number of multiplications for the chain of matrix from A4 till A6. That means we want to print the value at this position M4,6 represents the minimum number of multiplications which are being required to multiply the sequence of matrices A4 multiplied by A5 multiplied by A6. That means M46 means 4 from A4 through A6. How many counter multiplications are being required? This is the representation for the same. In general form, we can say minimum number of multiplications which are needed to multiply ai through aj, where ai is less than j. And if I is equal to j, that means only one matrix is being involved, then the cost of multiplying number of multiplication is 0, because nothing is being multiplied there itself. Now considering this example, how will be proceeding further for the algorithm of matrix chain multiplication using dynamic programming. For that purpose, we will be storing the partial results in the form of some array. This is a two-dimensional array. Let the array name is being given as M array. If you want to multiply the matrices, say total 8 matrices in the form of chain A1 multiplied by A2 and multiplied by A8. Total number of matrices are 8. That is a chain of matrix multiplication. For that purpose, we'll be creating an 8 by 8 dimensional 2D array. And what you will be trying to do here, you will be only filling the values including diagonal and upper diagonal values only in this. Now, how to fill in we'll discuss in the subsequent slides. Now, how this algorithm will proceed further, we will be entering the values diagonal by diagonal. That means first this diagonal values will be filled. In next iteration, the immediately adjacent diagonal will be filled. In next iteration, and next diagonal, next diagonal, next diagonal, and so on till last value is being filled. This last value is the minimum count of the number of multiplication which are being required to multiply this chain of matrices. Now this here will represent the number of rows and J will represent the number of column. If you are focusing on one, if you're concentrating on one element of this array, so this array, this value represents the basically M3J. This is M3J. This value represent basically M36. What this M36? It is the cost minimum number of multiplications which are being required to multiply the matrices, chain of matrices A3 into A4 into A5 into A6. That is from A3 through A6. Now moving further, this is a general formula which will be used throughout this matrix chain multiplication for solving the same problem using dynamic programming. Now let us suppose there is some partial result where you want to multiply chain of matrices ai till aj, and there is one kth index for which is giving you the optimal result. Now what to do, this partial chain of matrix multiplication is giving you some partial matrix which is of dimension 2 by 3, and 100 is the number of cost of multiplication which are optimal one, number of multiplication which are being required to generate multiply the matrix ai multiplied by ai plus 1 till ak. Similarly, the other partial set of matrices is aik plus 1 till j, and the dimension of that partial matrix is say 3 by 4, and the cost of multiplications which are being required to multiply this sequence of matrices is, let us suppose it is 200. Now the what formula says for matrix chain multiplication that for the array the entry for mij, jth entry will be equal to mik, that is the cost of multiplying the sequence of matrices till k index from I till k index, plus the cost of multiplying the matrices from the sequence ak plus 1 till j, plus the cost of multiplying these two partial matrices. What is the cost of multiplying these two partial matrices? That is 2 into 3 into 4. Now basically if you write in the form of algorithm point of view, this will be pi minus 1 because pi minus 1 will be the dimension of this, and the last column value will be represented for this partial matrix will be pj, and the intermediate dimension will be will be signified as pk. Now this is the general formula which will be used for solving the same problem using dynamic programming problem. Now if I is equal to j in general form, that means only one matrix is there. There is no multiplications are being there within that. That will reflect 0. Otherwise, we will have to find the minimum value by taking the k value, minimum of all these mij's, by taking that k value which is equal to I. That means first element is being included till less than j, that means for the last element is being excluded in that. Now taking one example, now given an example where some set of elements, now given an example where four matrices are being given with their dimensions, our problem is to get a particular order which will our goal is to find the optimal order in which these matrices should be multiplied to get the optimal value for the minimum optimal value for the number of multiplications. Now how to solve that? Go step by step for that. For this purpose, we are creating an array where we will be initializing the first value will be initialized as 0, 0, 0. This means m0, 0 means m1, 1 means the cost of multiplying the matrix that is merely first matrix A1, because there is no single matrix, no multiplication is being involved, that is why the value here is 0. Similarly, for 2 by 2, m2 by 2, the value will be again 0 because single matrix A2 is involved. For 3 by for m3 by 3, single matrix is being involved, no multiplication is there, the value will be 0. For 4 by 4, no multiplication is being involved, the value will be 0. That means all the diagonal entries will be 0. There is one more additional array S which we will be maintaining for the same. We'll discuss in the subsequent slides. What is the usage of that? Now, considering the now the considering now considering the case Now considering the case of multiplying the sequence of matrices with length is equal to 2. Length 2 means exactly two matrices are involved in multiplication, like A1 and A2. There different combinations can be A1, A2 of length 2. That means two matrices involved. A2, A3, only two matrices involved. A3, A4. These are three possible combinations for multiplying the pair of two matrices, for multiplying two matrices. Now, if you are multiplying A1 and A2, what is the final cost? What is the number of multiplications which are being involved in multiplying these two matrices? That is equal to M12. M12 means the cost of multiplying the matrices from A1 till A2. That is equal to M11. If you could use this formula, here K is equal to 1, M11 plus M22. That means cost of multiplying the first matrix with single element plus cost of multiplying, that is the cost of multiplying the matrix single matrix, and cost of multiplying the second matrix, and cost of multiplying these two matrices. Now, cost of multiplying these two matrices will be 40 into 20 into 30, and this value m11 and m22, as you know from the table itself, they are 0 because single matrix, it doesn't involve any set of multiplication. The result for the same is 24,000. Similarly, going to the second step, cost of multiplying A2 matrix with A3, that is represented by M23, that is coming out to be 6,000. Similarly, for the third case, A3, A4, that is coming out to be 9,000, and so on. Now fill in all the entries of M array, like here we have filled in 24,000, 6,000, 9,000, and we have filled in the entries of this array here as 1, 2, 3 and 2, 3, 4. The first entries of array will be 1, 2, 3. We'll discuss in the subsequent slide what is the usage of this array and why we have entered here 1, 2, 3. Now chain length 3 means that is the next step. For chain length 3 means that means we will be using three matrices in a sequence. Now we will be doing a group, taking a group of three. What are the possible combinations? The possible combination for the same are, let us suppose for the first case, the possible is it is A1, A2, A3. Second group can be A2, A3, A4. Now, if you want to multiply these three matrices A1, A2, A3, what are the possible combination which you can multiply? You can multiply A2, A3 first, then the result can be multiplied with A1, or you can multiply A1, A2 first, then the result can be multiplied. Result of the resultant matrix can be further multiplied by A3. Now, these are two possible variants. Out of these two possible variants, the variant which will be giving least cost of multiplication, that is the minimum number of multiplication, that will be picked up by the dynamic programming, that will picked up finally. Now, how to find the cost of multiplication for this scenario? That is, this A1 represent that cost of multiplying, M11 represent the cost of of using the cost of for matrix A1. M23 designates the cost for multiplying the matrices A2 and A3, and this is the cost for multiplying this A1 with the partial matrix A2, A3. Now, what is the dimension of A2, A3 matrix? That is 20 by 10. That means this is the cost. That means this is the cost for multiplying 40 by 20 matrix with the matrix 20 by 10. That is equal to 40 into 20 into 10. Get the sum and get the result. Similarly, A1 into A2 means that is cost of multiplying the matrix A1 till A2, and this is the cost of single matrix, that is A3. And this is the cost of multiplying this factor a1 a2 with a3. This we are getting the cost here like this. Similarly, going to the next group of multiplication like a2 a3 a4, two combinations are further possible: a2 into a3 a4 or a2 into a3 then a4. Going in the same direction, you will getting this result. Out of these, in the first case a1 a2 a3, that means m13 will be minimum of these two cases, but minimum value you are getting 14,000. So you will fill in the value as 14,000 for the 2D array 1 2 3. This 14,000 is filled in. For M24, minimum of these two patterns, we are getting the value of number of multiplication being minimum being 12,000. We will fill in for 2, 4, 12,000. Now, what this array, what we are attaching along with that is what is taking into account. That is, this array records the index k at which the product aij till ai till aj is splitted. Now, what this means to say that for S2, 4 is 3 means that means the best split is third uh, at the third index matrix. That is best split is somewhat here. This three value says. Now S1, 3 is 1 means S1, 3 is 1 means for the mat for finding the sequence of matrix A1 till A3, the best combination is of 14,000. 1 to 3 means 1 to 3 in the chain of matrix multiplication from A1 to A3. The best split is at 1. 1 means after this one index there will be splitting. This is how we can find from this S array, we can find that pattern in which or the order in which the matrix should be multiplied such that it leads to minimum number of multiplication. Now further moving for now moving further for the chain length is equal to 4. We'll again trying this algorithm. Now M1, 4 means we are involving all the four matrices into account: A1 into A2 into A3. What are the possible uh, patterns which are what are the possible orders for the same? A1 multiplied by A2 A3, then A1 and A2 should be multiplied, A3 should be multiplied, then A1 A2 A3 should be multiplied like this. True groups are there because we have to find the minimum out of these two cost values. Two groups means these are the two cost values which would be involved in the internal algorithm manipulations. Now, when we are for the first case, A1 and cost of multiplying A2 to A4 is M24. Here, the cost of multiplying A1 A2 is Here the cost of multiplying A1 A2 is M12. Cost of multiplying A3 A4 is M34. Here cost of multiplying A1 till A3 is M13, and cost of multiplying the individual element is M44. That value is 0. Now, out of these three possible patterns or orders of multiplying the matrices A1 till A4, this pattern, that is first multiplying A1 with A3, then the final result of this will be multiplied with A4 is giving the least value, that is 26,000. Therefore, this value is being M14, which is the minimum of this, is being entered at the last location. This is the last step of this algorithm. Now this whole of this array, this basically represent that last value, that is A14 here represents the minimum number of multiplications which are being required to multiply the matrix, the chain of matrices from A1 till A4. And what is that order? That is being will be represented by this S array. Now here in the entry, this 3 represent here from S1 to S4. That means when you are multiplying the matrices from A1 to A4, S1 to S4 will give the ordering for multiplying this chain of matrices from A1 to A4, such that the 3 signifies that out of these 3 patterns, this is the optimal one. That means this ordering is the optimal one. At third matrix index matrix, this is third, there is a splitting. The splitting is being done here. This is what this array is interpreting. Now what is the order? Now you got the minimum number of multiplications. Now what is the ordering of the matrices, in which order that matrices should be multiplied to get this minimum count of multiplications? How to retrieve that from S array? We have, once we got the result, the array which is given to us, now how we can find the ordering of the vertices? No doubt we have got the result that minimum number of multiplications which are required to solve this chain of matrix chain of to solve this chain of matrices multiplication, that is 26,000. But what is that order? How to extract? We, for that purpose, we will take into account this array, that is a S array. Now first we will try to split this whole of the chain matrix chain at a particular location. Now how to find at which point we have to split this chain is that if we are considering whole of this sequence of matrices, that sequence of matrix is from A1 to A4. Now we will first look into the entry in the same for the same in the array S1 to 4 only. Now what is the entry in S1 to 4? That value is 3. Now this value 3 says that after the matrix with index 3 we have to do the splitting like this. That means for S1 to 4, that after 3 we have to do the splitting like this. Now once it has been splitted, now how to perform the matrix multiplication, what order should be maintained for multiplying the matrices from A1 to A3. Now for finding the order for multiplying the matrices from A1 to A3, for this chain or sequence, we'll look into the entry S13 because we want the splitter for 1 to 3 range. Now what is the value from 1 to 3? That is basically 1 within the array. That means we will be doing splitting somewhat here after one index matrix. So that means this whole group A1, A3 will be further divided into two groups. One will be having A1, another will be having A2 and A3. Like this, A1, A2 and A3 and A4. That's all for the ordering. This is the final value of the ordering. Now if you want, you can just cross verify how the value of 26,000 had come. We will try to find that number of multiplications step by step. As you know, first A2 and A3 will be multiplied. A2 and A3 is being multiplied. Now what is the cost of multiplying these two matrices A2 and A3? That is nothing but 20 into 30 into 10. That cost will be 20 into 30 into 10. Now after multiplication we are getting some matrix, and that matrix will be multiplied with A1. Now what are the dimensions of A1? That is 40 into 20. And what are the dimensions of this matrix, which is A2, A3? That will be 20 into 10 after multiplication. That is, we are multiplying 40 into 20 with 20 into 10, and the cost of the same will be 40 into 20 into 10. Now once we got this matrix will have dimension from A1 to A3. This matrix will have dimension 40 into 10. This 40 into 10 matrix will be further multiplied with the matrix 10 into 30. The cost for the same will be 40 into 10 into 30. Now combining all the costs, we will be getting the result as 26,000. That's all for the current session.